Prestige worldwide. Prestige worldwide.
We're Group 7, Prestige Worldwide. We did our project on solar thermal fluid heating. I'm Michael Brushett.
I'm William Dudley.
I'm Daniel Gillard.
I'm Damien Ryan.
And our project supervisor was Dr. Yuri Muzichka.
All right, a little bit about what we're going to talk about today. So on the agenda we have our project management plan, problem definition. We're going to move on to some of our design constraints and criteria. Then we're going to get into some background research on our project, which will include what exactly solar thermal fluid heating is and some of the project history. Then we're going to move into our design, concept generation, and preliminary concept description. So, our project management plan. So, we essentially follow an 8-step process, which can be shown below. The first phase of the project included our problem definition, research, concept generation, and preliminary design. And into the second phase, which we are currently on to now, is into our prototype and actual design fabrication. So here's our project management plan, which can be a little bit hard to see. The main points we want to take from this is that we're on schedule for our project coming into the first week of March, which comes into actual fabrication of our design and testing in the next few weeks. So our problem definition for our project. As a group, we decided that our problem definition was going to be to complete a final system integration of all major components of a 2-phase solar thermal fluid heating system. We essentially divided the project into 3 separate parts. The first part being the design and fabrication of our mobile testing unit. Then we're moving on to optimization of different subcomponents to improve the overall system. And thirdly, we went into a conceptual design of a secondary indirect heat exchanger for cold climates such as Newfoundland. So, some of the design constraints, which all groups have been considered with, was the project must be completed in a 3-month time frame. We're limited to a cost of $500, $250 from MUN, and $250 from ourselves. The testing unit must be mobile, and the solar panel must be able to rotate 90 degrees in 2 axes. And we also must be able to have a system where we have 2-phase flow, which includes liquid and gas. So some of the design criteria which we based our design around, we basically needed to have maximum sunlight exposure to have the greatest efficiency of our solar panel. The mobile testing unit must be very compact for close quarters. All components of the system must be able to fit inside the case, so that will include the oscilloscope, heat exchanger, pumps. The testing unit must be able to be operated by one single person. It needs to be able to easily maneuver it around the lab downstairs and get out to the doors. And it needs to have a simple design for easy manufacture and setup.
So the next thing we moved on to was our research. And the first question you might have is, what is solar thermal fluid heating? Solar thermal fluid heating is a process that collects energy from the sun to heat a fluid. As you can see here, if you're in the field on a nice sunny day, you have your solar collector. This is the solar thermal collector here in black. And the heat from the sun is actually solar radiation. Solar thermal collector will collect. Here we have a more detailed diagram. As you can see here, the solar thermal collector is essentially a rectangular box with a transparent top. The sun's rays enter the box through the transparent top. And on the left-hand side, you have your cold water coming through your inlet, and this will travel through several passes of piping, and where your water will collect the sun's heat. On the outlet side of the box, on the right-hand side, your warm water will exit, depending on how many passes of your piping. This will determine your temperature. Some uses for solar thermal heating. As you see here, we have a household solar thermal collector on the top. It can be used for heating your floors, your washing machines, dryer, shower, sinks. Basically, it heats the water in your hot water tank to be used anywhere in your house. So a little bit of project history. This project actually builds on 2 previous projects. The first being Nova Solaris. Nova Solaris designed and fabricated a single-phase solar thermal heating system, and they tested the efficiency of a single-phase liquid system. As you can see here, this was the original system setup for Nova Solaris. We basically had one pump with a solar panel and a 25-gallon tank reservoir, and they specifically tested for single-phase efficiency. The next group to take on this project was Solar Thermal Solutions. They built on work from Nova Solaris, but they modified the original single-phase system into a two-phase system, which was liquid gas. They tested the effectiveness of injecting gas bubbles into the liquid flow to improve the efficiency of the heat transfer from the solar radiation to the water. This was the Solar Thermal Solutions setup. As you see here, they had the pump, 25-gallon tank, and solar panel from Nova Solaris, but they added in a three-way air injection manifold, solenoid valve, and a compressor to add the gas bubbles into the liquid stream.
So for our project, our main objective was design and fabrication of a mobile testing unit. So we used 8 design criteria when generating concepts for our mobile testing unit. These were sunlight exposure, stability, weight, maneuverability, simplicity, durability, storage space, and cost. So using these various features, we then ranked 7 components of the testing unit. This includes the mount material, the mount placement, rotation of the mount, case material, case movement, case shape, and case size. So we moved forward and generated some concepts. This is concept number 1. It has a rectangular shape and a top mounted panel. There's a wooden case, mount and leakages. There's carbon steel pins for it to move about. The panel orientation can be changed with the varying linkage location. And there are 4 rubber wheels which are lockable. Pros of this, it is very sturdy and compact, and cons are it has an increased complexity due to the linkage design, and it is hard to set up. Concept 2 is a rectangular shape and a wooden case. It has a steel mount and a side mounted panel, and has 4 inflatable tires. The pros of this is the rotation of the mount, and it is quite simple. The cons are it is unstable due to the front mounted panel, and it is hard to maneuver around the shop due to its added width. Concept 3 is the one that we move forward with. It has a rectangular shape and a wooden case. It has a steel mount and connecting plate. It has an elevated panel for maximum sunlight exposure and has plastic wheels. Pros of this is the rotation of the mount, and it has maximum sunlight exposure. It has a simple design and is quite stable. Cons is the increased height. So you see here our concept selection, where we went with the weight, size, ease of manufacture, simplicity, all the things that went with deciding which one we're going to move forward with. We used concept 1 as our reference, and each concept then was based on a plus-minus system, and it turned out that concept 3 was the better of the 3.
Here is a prototype of our model done in SolidWorks. It shows the 3 degrees of freedom that the panel can move about. One being here with the pin allowing the panel to tilt, and then another pin in the middle of the mount allowing the panel to rotate. And the 3rd degree of freedom would be when the wheels get attached to the bottom of the case on the bottom, and allow the entire system to be moved. So next, we'll talk about the optimization of the system and the subcomponents. So for the optimization of the system, we'll be looking into the sizing of the pump and the sizing of the compressor to find the most optimal one for the panel that we have, and also improving the gas bubble two-phase flow. Next is the concept design with the added heat exchanger. So here's a schematic, similar to what there is now. Glycol will be used, pumped into the air injection manifold, where the air bubbles will be introduced, producing the two-phase flow. Will run through the solar panel, as it does now, and through the glycol tank and pass to the heat exchanger. As the glycol passes to the heat exchanger, a secondary loop of water will pass to the heat exchanger, and the heated glycol will heat the cool water and be be pumped into the water tank or would be used for in-floor heat. Thank you for listening. Is there any questions?